Hi everybody. I wanted to do a quick video that would help, I think, clear up some misconceptions people have about Gauss's law problems. I got a feeling that most of the class is doing really well. There's not a whole lot of problem with the Gauss's law type problems that we're trying to do. But I got a feeling there are some misconceptions that are going to throw some people off and maybe really just mess a whole lot of people up. So what I want to do today is to get some of those misconceptions cleared up. Now, and comes about in the problems that you have to submit, also the writing assignment that we did on the linear charge and the cylinder versus the box for the Gaussian surface. So I'm hoping that we can clear that up. Now, a problem like that one that we did on the writing assignment with the long linear distribution of charge that was infinitely long, and we had to use a cylinder. Some people had a misconception about how to even start that kind of thing because they didn't know where the charge was. So luckily, I have an infinitely long linear distribution of charge that I brought with me today. So just one second. Okay, here it is. Infinitely long linear distribution of charge. And the problem that we're trying to solve is, what is the electric field a distance r away from this? So we're looking right here. What's going on at a distance r, constant distance r, some point away from this charge? Now, this is the charge. The charge is all on this linear distribution of charge. No matter what we do, it doesn't move the charge. The charge is here. Don't forget that. So we're trying to find some way to figure out what's going on right here. And what we use is a cylinder. Why do we use a cylinder? There's two reasons, and this is what's on the writing assignment. The first reason is we want to find out what's going on at distance r. So we need to use some kind of a shape that's going to allow us to be measuring electric field at a constant distance r. Now if we use a box, then some of the corners of the box are going to be farther away, and then the sides will be closer, and then the next corner will be farther away. So as you go around the box, the distance constantly changes. And if you don't believe that, just draw a little dot and put a square around it and look at all the distances away from the middle of a square. The corners are farther away than the sides are from the middle of the square. So you can't use a box. You got to use a cylinder. So luckily I brought along a Gaussian cylinder. Just one second. Alright, so here's my Gaussian surface. It's a cylinder, as you can see, and we put it right here, and this is going to allow us to measure the electric field at the surface of this cylinder, which is at a distance r away from the linear distribution charge. Now if we could put a top and a bottom on this piece of duct tape, then we'd have a closed surface, and we would be able to say, well, how much charge is enclosed? Well, the amount of charge that would be enclosed would be the amount of the linear distribution of charge that's inside the box. So if we could cover up the top, cover up the bottom, then the only thing that's inside the box that's charged is the little tiny piece of the stick that's about this long. There it is. It's inside the box. That's where the charge is. Putting this Gaussian surface here doesn't change the charge. The charge is on the stick, not on the cylinder, not on the Gaussian surface. So it doesn't matter. Take it away. The charge is here. Put it here. The charge is still on the stick. The second reason we use a cylinder is because we're going to have to do a dot product, and we're going to have to do an integral, neither one of which I really want to do. So what we have to remember is that the electric field is always pointing outward away from this infinitely long linear distribution of charge. So the electric field always points away. So what we want to have is something where we're going to be able to do the dot product of E dotted with the area vector, but not have to actually do it as a dot product, because none of us like to do that. So we pick a cylinder where the area vectors are also pointing away. So then when we line up the area vectors with the electric field vectors, the dot product turns into a nice, easy product, and we don't have to do dot products, which is what we like to do, not doing dot products if we don't have to. So then that makes the problem so much simpler. So we have to know that we can have the area vectors lined up with those electric field vectors. Now if we put a box here, the electric field vectors are still sticking outward because it's the same charge. But the box has this weird thing where on the sides it sticks out and sticks out and sticks out and sticks out. So that sounds good, but on the corners and on the edges they don't line up. And again, just draw a picture of a square and look at the area vectors. The area vectors are always going to be straight up and down or straight sideways on the side of the box, but they're not going to line up with the electric field vectors because the electric field vectors are always radial. So you have to have a cylinder. So then what do? Well, you just have to figure out how much charge is in here. You have to say it's got a height L, and therefore the amount of charge that's in here is just the amount that's included on this height L, and you need to know the area of this part right here, because that's where the flux is going through the electric field is creating flux because the electric field passes through the curved edge. So that's easy. That's just the circumference multiplied by the height, and that's your area. And then you can solve the Gauss's law problem. The problem people have is by putting this here, a lot of people are starting to think that the charge is on the Gaussian surface. It's not. The charge is here. Putting this here doesn't change it. I could put this, I could put a box, I could put a sock. It doesn't matter. The charge is still right here on this thing. So it doesn't matter. We can do another kind of distribution, like an infinitely long cylindrical shell. And luckily I brought one of those. Just one more second. Alright, so we have an infinitely long, almost, cylindrical shell. So this is a hollow cylindrical shell. So it has no charge in the middle, no charge on the outside, it's just on the shell. And where's the charge? On the shell. We put a Gaussian surface here. What happens? Nothing. The charge is still on the shell. It doesn't become on the Gaussian surface because the Gaussian surface is not real. It's just a tool that we use to do the problem. So how much charge is enclosed in this Gaussian surface? Whatever's on the shell on a height that big, because that's where the Gaussian surface is. Now we could use a Gaussian surface that would kind of be inside here if we want to use a smaller r, but of course if we did that there wouldn't be anything in there, so the charge enclosed would be 0 because none of the shell would be enclosed. When the Gaussian surface is bigger, meaning r is bigger than the radius of the shell, then all of it's enclosed, all of it being the amount that's on a part of the shell, which is that high if that's the size of our Gaussian surface. So that's how we do these problems. We got to figure out how much charge is enclosed. We use the Gaussian surface to find the area. Well, really it's the whole E times A for the whole thing, but it's always easier than that because we're always lining up the electric field vectors with the little area vectors. So we don't have to do dot products, we don't even have to do integrals. All we have to do is really calculate areas. But you have to know that they start from Gauss's law. Why do we pick this, not a box? Because constant radius, it's a circle. And it also has to have the area vectors lined up with the electric field vectors. I'm hoping that's going to help you try to get a good understanding of these Gauss's law problems. I got a feeling people can do them and not understand them. So I'm hoping you get a better understanding of what's going on. That way if you get something thrown at you that's a little weird, you're going to be able to handle it because you know what's going on. If you have any questions, email me before Tuesday and I'm hoping I can help you out. Cheers.